Sample Preparation and Sputter Deposition by Samantha Lanou, Alexander Barvanek, Sergio Brown, and Kaylee Lamb.
Before we get into the specifics of this laboratory investigation, it is necessary to provide some brief background information. So what is a TFT-LCD? The term TFT-LCD stands for Thin Film Transistor Liquid Crystal Display. Thin film transistor liquid crystal displays incorporate a thin film semiconductor layer which acts as a switch, providing voltage to a liquid crystal. A liquid crystal display is made of millions of pixels. Each pixel is composed of 3 subpixels, one for each color: red, green, and blue. Each subpixel has its own thin film transistor that varies the voltages applied at each crystal. This results in varying light transmitted at each subpixel. This allows for sharper, high-quality color images and also provides quick response times in touchscreen devices. TFT-LCDs are used in a variety of devices, including computer monitors, televisions, and smartphones.
The goal of the experiment. The goal of this experiment is to replicate the synthesizing process used in the transistors of liquid crystal displays. The first layer deposited on top of the silicon substrate was a silicon nitride layer. The next layer, co-sputtered on top of the silicon nitride, is the silver-copper layer. The purpose of the silicon nitride layer is to prevent diffusion between the silver-copper and the silicon substrate. Silver is notorious for the degradation of silicon-based semiconductor devices. Copper was used in order to achieve an encapsulation layer through the formation of oxides. Oxides were formed through the annealing process, which will be talked about later on in the presentation. Silver by itself is corrosive and has issues with agglomeration. The encapsulation layer of copper oxides used was a preventative measure. Aluminum copper is used in industry before, but now silver is preferred due to its low bulk resistivity of 1.47 microohm centimeters for higher current density and switching speeds. This is imperative to achieve clearer and brighter screen displays.
An RF sputter gun was used to deposit the silver-copper layers onto the silicon substrate layers. Sputter deposition is a physical vapor deposition method used to deposit thin films. This device uses high-energy ions to strike a target. By having an electric wave run through the argon gas, a plasma is created. Inside the plasma, the gas atoms lose electrons, turning them into positively charged ions. These ions are accelerated and collide with the target. The target contains the material intended to be deposited. These ions strike the target with enough force to dislodge the atoms off the target material. The released material then travels in the chamber until colliding with the substrate, where it is then deposited. In order to attain an effective coating of the substrate must be clean. This is because, in order for the deposited atoms to form a proper film, there must be good film adhesion on the surface. The sputter gun used in this experiment was the Lesker Supersystem 2, located in the Goldwater building at ASU. This device is a radio frequency sputter technique. RF sputtering is used as an alternative to DC sputtering since it alters the electric potential of the current under vacuum at radio frequencies. This is done to reduce inconsistencies in the film by reducing the arcing in the plasma. For this deposition, a nitrogen-rich vacuum environment was created in the chamber. To deposit the silicon nitride layer, 100 watts was supplied to the plasma gun for 5 minutes. For the silver-copper layer, each of the 2 plasma guns were given 100 watts of power for 6 minutes. The copper and silver were simultaneously deposited onto the wafer.
The annealing process.
The sample was required to be annealed in order to encapsulate the silver by the formation of copper oxides at the surface. Each of the 5 samples were annealed for a time ranging from 0 to 150 seconds. It is important to ensure that the crystal lattice parameters are similar when sputtering onto a substrate. Failure to do so may cause layers to peel and separate when annealing after a certain amount of time. Typically, the encapsulation process is conducted at very high temperatures and requires a significant amount of energy. Using microwave annealing allows this process to be carried out faster at lower temperatures and thus with a lower consumption of energy. The microwave used in this process was a standard kitchen microwave with the addition of a sensor to measure the temperature of the sample. Ceramic blocks were placed in the center of the microwave in order to raise the sample and therefore directly align the microwaves with the sample. Wafer cleavage process. During the synthesis of the wafers, the manufacturer will cut flats in order to indicate the scoring direction that is to be used. To cut the silicon wafer into 1 by 1 centimeter squares, you would use a diamond cutter to score the edge of the silicon wafer. This is because cleavage fractures occur along the 111 or 110 plane in silicon. Then, using 2 tweezers, grasp the wafer on both sides of the cut and apply pressure downward to cause a fracture. Continue these steps until you achieve the 1 by 1 centimeter squares.
Summary. In summary, the goal of this experiment is to replicate the synthesizing process used in the transistors of liquid crystal displays. In the thin film deposition process, each layer was employed for a reason. The silicon wafer served as the substrate. The silicon nitride layer served as a diffusion barrier. Lastly, the copper oxide layer served as an encapsulation layer. The Lesker Supersystem 2, a radio frequency sputter deposition system, was used to deposit these layers onto the silicon substrate. We also covered the cleavage process, which was done using a diamond crystal to score the wafer surface in order to achieve 5 1 centimeter by 1 centimeter square samples. Furthermore, microwave annealing was done to encapsulate the silver by the formation of copper oxides at the surface.
That's a wrap.